Netflix is saving roughly 90% of their compute time on certain data pipelines, and the trick is something called incremental processing. Let's get into it.
Yeah, and that number is real. They published the before and after. A two-stage pipeline that used to take about 10.5 hours total now runs in around an hour. Same business logic, same Spark settings, just a fundamentally different approach to which data you actually touch.
Okay, so before we get to the how, let's set the scene. What's the problem they're solving?
So Netflix runs enormous data pipelines. Think playback events, A/B test results, content acquisition signals, payment fraud detection. All of that flows through batch workflows, and the classic headache in batch processing is late arriving data.
Late arriving data meaning like your phone was offline and then synced later?
Exactly. A user watches something, the event sits on their device, eventually it phones home. By then the daily pipeline already ran, so now yesterday's numbers are wrong. The naive fix is what they call a look-back window.
Which is just reprocess the last n days every single time the job runs.
Right. You pick a number, say 14 days based on domain knowledge. We're pretty confident data older than 2 weeks isn't going to show up late. And every day you just chew through 14 days of data even though, as the article points out, late arriving data is sparse, maybe a few % of the total.
So you're doing 14 times the work for a few % of the actual new information.
Exactly, and it compounds because these pipelines have stages. Stage 1 produces a table, Stage 2 consumes that table. Both stages have their own look-back windows. The waste stacks up fast.
Okay, so what's the better idea?
The better idea is only process what actually changed, which sounds obvious, but the hard part is tracking what changed in a way that's lightweight, accurate, and doesn't require you to rewrite all your business logic.
And this is where Apache Iceberg comes in.
Right. So Iceberg is a table format for big data. One of its key properties is that every write to an Iceberg table creates a new snapshot. A snapshot is essentially a pointer to a set of immutable data files. The old files don't go away, you just add new ones and update the metadata.
So you have a built-in history of what changed and when.
Exactly, and the metadata for each data file includes things like the upper and lower bounds of values in specific columns. So you can look at two snapshots, compare them, and know not just which partitions changed but also the range of values, like which date ranges or account IDs are represented in the new files.
Without actually reading the data files themselves.
Without copying a single byte of actual data. That's the key insight of what they built. They call it an ICDC table, Iceberg Change Data Capture. It's a new lightweight Iceberg table that just holds references to the new data files from the original table. No data duplication.
So it's like a diff, a pointer to what's new.
A pointer to what's new. And because it's itself a valid Iceberg table, your Spark job can just read it like any other table. You don't need special connectors or custom code in your pipeline logic.
That's elegant. So how does this plug into Maestro? Because Maestro is Netflix's workflow orchestration system, right?
Yes, Maestro is their internal workflow as a service platform. Think of it as the engine that schedules and runs tens of thousands of data workflows for data scientists, engineers, analysts, all kinds of users. The article says it fully migrated all workflows onto Maestro with minimal interruption.
And IPS, the Incremental Processing solution, is built on top of Maestro.
Built as an extension, yeah. They added 2 new building blocks, a new trigger mechanism, and a new step job type. When a workflow uses IPS, Maestro automatically injects a parameter into the workflow pointing to the ICDC table for that run. The workflow just reads that table name and processes whatever's in it.
So the user doesn't have to wire up the change capture logic themselves.
Minimal changes to existing pipelines. The article specifically calls out that the user's business logic is decoupled from the IPS implementation, which is a big deal for adoption. You're not asking engineers to redesign their ETL from scratch.
Let's walk through the concrete example they give, because I think it makes this really tangible. It's a playback events pipeline, 2 stages.
So the original pipeline. Stage 1 is a daily workflow that reads 14 days of raw playback events and writes transformed data to a target table, overriding the past 14 days each time. That takes about 7 hours.
7 hours every day, reprocessing 14 days of data.
Every day. Stage 2 then takes that output table and aggregates it. Also reads 14 days, also overwrites. Another 3.5 hours, so roughly 10.5 hours of compute, most of it redundant.
And in the new version?
Stage 1 now reads the ICDC table for playback events, which only contains the new and late arriving files since the last run. Instead of insert overwrite, the job does AMERGEINTO, so it surgically updates only the affected rows in the target table. That stage drops from 7 hours to about 30 minutes.
That's wild. Same Spark settings, same business logic, just a different input and a different write pattern.
And Stage 2 gets similar treatment. Because Stage 1's output table is also an Iceberg table, IPS can create an ICDC table for it too. Stage 2 joins the original data with the change capture table on the aggregation group by keys. So for late arriving data, across days 2 through 14 it only processes records tied to accounts or keys that actually changed. That stage drops from 3.5 hours to 30 minutes total.
So the whole pipeline goes from 10 plus hours to about an hour.
And the article frames it as roughly 10% of resources compared to before, measured by execution time. They're careful to say the Spark job settings are the same, so it's an apples-to-apples comparison.
Let me ask about something that seems tricky here. You mentioned there are different patterns for how a workflow might use the change data. Not every pipeline is a simple pass-through.
Good catch, yeah. They describe 3 patterns. The simplest one is what we just talked about. Change data carries all the info you need, you process it and merge it downstream. Basically a direct replacement for look-back windows.
What's pattern 2?
Pattern 2 is for aggregation jobs. If you're grouping by, say, account ID, then when a new row arrives for a given account, you need to re-aggregate all the rows for that account, not just the new row. The ICDC table tells you which account IDs have new data. You then join the full source table with the ICDC table on those keys to filter down to only the relevant accounts. Big speedup, but no change to the actual aggregation logic.
Clever. And pattern 3 is the complicated one.
Pattern 3 is for really complex cases, like multi-table joins or window functions where you need a range of data reprocessed rather than specific rows. The ICDC table there gives you range parameters, upper and lower bounds from the Iceberg metadata, which get injected into the workflow as parameters. So instead of reprocessing the past 14 days by assumption, you reprocess exactly the date range that's indicated by the change data.
Which might be just 2 days instead of 14.
Exactly. And the article makes the point that this is fundamentally more accurate than a hard-coded look-back window because it's derived from actual data, not from someone's best guess about how late data might arrive.
Okay. I want to ask about data accuracy specifically, because this isn't just about speed, there's a correctness dimension too.
Right, and this is subtle. With a look-back window, you're making a bet. You say late data won't arrive after X days, but you might be wrong. With IPS, because you're tracking actual file-level changes, if data arrives late, even unexpectedly late, the ICDC mechanism captures it and your pipeline will process it. You're not relying on a human's estimate of data latency.
There's also a point in the article about micro-batch scheduling. That's a freshness story, right?
Yeah, data freshness is the third leg of the stool. Because IPS workflows are cheaper and faster to run, you can afford to run them much more frequently. Instead of once a day, maybe every 15 minutes. That's what they mean by micro-batch scheduling. You get near real-time freshness from a batch architecture.
Without having to build a streaming pipeline.
Which is a much bigger engineering investment. This is a nice middle ground. You keep the simplicity of batch semantics but get much lower latency.
There's a fourth topic the article mentions but deliberately punts on, backfill. What's the basic idea there, even if the details are coming later?
So backfill is when you need to repopulate historical data. Maybe your business logic changed, or an upstream dataset got corrected. With the old approach, you'd have to manually build backfill workflows for every stage of your pipeline, which could be days or weeks of work. The article says IPS can propagate backfill automatically downstream because the change capture mechanism naturally picks up the upstream changes and triggers downstream workflows. They're calling it one-click managed backfill, but the full design is coming in a follow-up post.
One thing I want to flag, this is all built on Iceberg specifically. If you're not on Iceberg, you don't get this.
That's fair, and the article doesn't address non-Iceberg tables at all. It also doesn't say anything about how they handle tables that aren't purely append-based. They actually call that out as future work. Right now, IPS works cleanly for append-only scenarios, and they're working on supporting other change types like overwrites.
Last question, what's the adoption story? Is this something teams opt into, or is Netflix pushing everyone toward it?
The article positions it as opt-in but with very low friction. Because business logic changes are minimal and the IPS features are injected by Maestro rather than requiring custom library code, the migration cost is low. And compared to older internal solutions like one they mentioned called Cyberg, which were tightly coupled to user business logic and had high migration and maintenance costs, this is much cleaner. The decoupling is really the architectural win here.
80 to 90% compute reduction by only processing what actually changed. Sometimes the most powerful optimization is just doing less work.